Welcome everyone to the online lecture of CSE 4551 Computer Graphics and Multimedia. Uh, Today we'll be talking about ray tracing. This is part 1 of a two-part lecture on ray tracing. Previously we had talked about ray casting in our previous video, which allows us to simply and accurately render diffuse surfaces. But as we have said before, it does not handle some realistic phenomena like shadows, reflection, refraction, and caustics very well. uh, I think we have already said this, talked about these few phenomena that cannot be handled by ray casting in our previous lecture. And for that, we said that we would need ray tracing, and that's what we will be talking about in this lecture. So here we have a separate rendering algorithm that can handle these cases, and this algorithm is known as ray tracing. This is basically just an extension of the ray casting algorithm. Uh, or you can say that raycasting is a specific version of the more general algorithm that is ray tracing. Today we'll be discussing how features like shadows, reflection and refraction are handled in ray tracing, but we will not be talking about caustics here since this particular feature is not fully handled by ray tracing, but rather it requires another topic, that is global illumination. So these are the main topics we'll be discussing today. We'll start with shadows. So refer to this pseudocode. The code may look complex at first. Here, this is the pseudocode that I was talking about. This code may look complex at first, but it is pretty easy to understand once you ignore some of the lower level functions and focus on the main steps here. Notice that the very first line that gives us the color here is basically what we got from ray casting. This line. This is just simply what you would get from the material of the object once your ray hits it. You just get the color value. But all the things that happen after it are just the additions that are done for ray tracing. And this addition allows us to just introduce shadows into our scene. So if you have understood ray casting and how ray plane or ray sphere intersections work, then we already know how we reached up to this point. The next part is what is newly added for ray tracing. For ray casting, finding the intersection point and then the color of the material at that point was enough. This for ray casting, this would be the end. But now we extend it so that for every light source in the scene, we will have secondary rays. Well, for every light source, we are saying because there may be multiple light sources here. It's not necessary that only one light source will be present in the scene. There may be multiple light sources. For this, we extend it for every light source. We cast secondary rays from the and we call these rays as shadow rays. We cast these rays from the intersection point towards the light source. These rays are basically represented by the ray object ray2 in the pseudocode. Now for every object in the scene, we compute the intersection points with the shadow ray ray2. And getting the solution t values, if we find that it is equal to the distance to the light source, then there is no other object intersecting with the shadow ray except the light source. Then it means the initial object should be illuminated. That is, if you cast a ray from the intersection point towards the light source and you see that no other and the t value that you obtain does not is not smaller than the distance, that means the t value was obtained right at the end, that means at the light source, then that means there was no other obstruction in between. So that means this particular point should be illuminated fully. That means it's not in the shadow. And by illumination, we basically mean that adding the light source's illumination factor into the color value of the initial object when shading. Otherwise, if we find that the shadow ray intersects with another object before the light source, then the initial object is in shadow, so we set the color to black or gray. Well, there is a particular phenomenon, particular visual artifact that is seen when computing shadows using the previously mentioned technique we talked about before. And this artifact or particular bad phenomenon is known as self-shadowing or shadow acne. Notice the small black dots on the left image. Why do you think this happened? Recall that in the previous lecture when we talked about finding the ray plane and ray sphere intersection, we had to find the values of t, which could be a floating point value. And we know that numbers in the 3D engine or in any digital system can only be represented within a certain precision. And sometimes the intersection point may not always be directly on the surface of the object, but rather slightly inside the object. For example, suppose when you're calculating the intersection point here by solving the ray and the sphere surface equation, you get a particular value for t here, but this t may not determine the exact point on the surface, because t, when you're determining t, you're having some round of errors. So the solution that you get, that particular point may be inside the sphere a little. So because of that, when you cast rays from this uh, from inside the surface of the object, then the ray will obviously intersect with the surface at first before reaching the light, right? So notice this crucial point here. If this small rounding error occurs, the intersection point becomes inside the surface. Then the shadow ray cast from that point towards the light source will obviously intersect with its own surface at first. Thus, that region of the surface is mistakenly thought to be under the shadow of another object, and this is known as self-shadowing, because here it is not actually under the shadow of any other object. It's actually getting shadowed by its own surface. So different methods can be used to alleviate this problem. One solution is to use double precision instead of single precision, so that the solution t values are more accurate and so is found right on the surface. But this does not eliminate the problem totally. It just makes it less likely to happen. Another simpler and more robust solution is to systematically displace the origin of the shadow ray by a small epsilon amount. That is, here when you are calculating the intersection point, before calculating the intersection point, you displace it by an epsilon amount. The shadow ray will be its origin will be displaced by an epsilon amount, a very small amount that can be tweaked, so that the shadow ray is never originated from inside the surface. It's always guaranteed to be originated from outside the surface. And this epsilon amount will be displaced along the surface normal, so that the small rounding error can be cancelled out. This displacement value here is otherwise known as shadow bias. Now you might be thinking that we could have easily avoided the self-shadowing problem by not considering the object itself from which the shadow ray is being casted. So another implementational trick is to simply keep track of the object from which the secondary shadow ray got originated, and to exclude that object itself when computing the intersection of the shadow ray with the light source. For example, exactly at this point when we are considering for every object, we are calculating the intersections with the shadow ray. Here we could have actually excluded this object itself when calculating the intersections, but there is another reason why we don't do this. There is a complication here if you do this. That is why we avoid it, because think of a scenario where the shadow ray hits a part of the same object from which it got originated. So for example, okay, so now consider a scenario where the object is not spherical, rather it's C-shaped, and a light comes towards the concave part of the object, and at that point you have to calculate the shadow ray towards the light source. Now, while casting another ray, shadow ray, towards the light source, that particular ray intersects with another part of the same object, the upper part of the C object. So the lower part then should be under the shadow of the upper part, but that won't happen if you exclude the object itself, when casting the shadow ray. So for example, this can actually be more easily visualized. For example, try to match this scenario with you holding your hand in front of your face, so that the light from the light bulb doesn't reach your face. thus creating a shadow of your hand on your face. Suppose the primary ray would at first hit your face, and then you are considering shadow rays from your face towards the light bulb. If during this step you remove your own self from the object list to avoid self-shadowing, then the fact that your own hand is should cast a shadow on your face will not be handled, and your face will get illuminated fully even though your hand is covering your face from the light source. So that is why that is the problem that would happen if we exclude the object itself uh, when considering the intersections of the shadow ray with any other object, or whether if there is any other object before the light source. So that is why we stick to the use of epsilon here. Another technical detail uh, we should note here about the shadow ray is that unlike the primary camera ray we used in ray casting, we do not need to find the closest real intersection. Closest real intersection here. Just any intersection will do. So instead of calculating all the solution values for t, it is enough to stop after getting a single real value for t. Thus, it is possible to obtain a small amount of performance boost. So this is just a kind of optimization uh, detail that we should think about with shadow rays, and that is that we do not need to consider, we don't need to exactly find where the intersection occurred. We just need to know that an intersection occurred. Okay, then we move on to another topic, and that is reflection. We have already added shadows to our rendering mechanism in the previous section. Now we add another feature to our ray tracer, and that is reflection. Reflection in a ray tracer follows similar rules to the real world optics that we know of. The main difference is that physics tells us that our vision of a reflected image comes by light bouncing from the surface of an object. From the object, light comes and gets and hits a mirror surface, then it gets reflected and it reaches our eye, and that's how we get vision of that object through that through the reflection. But in case of ray tracer, we simulate the reverse. That is, the ray is cast from the eye or camera towards an object with reflective material, from the eye towards an object with reflective material, and then another ray is cast from that point of the reflective object symmetrically by following this angle. Then another ray is cast towards the other objects in the scene. So this is the reverse mechanism that is followed for ray tracing. In real life, the actual thing that would happen is light coming from the light source would hit the object. It would get bounced back from here onto a reflective mirror surface. Then it would come to our eye. But here, in case of graphics, computer graphics, in a ray tracer, what we do is we cast rays from the camera towards the reflective surface, and then we cast another ray from the reflective surface towards the objects. Here the reflection coefficient Ks determines whether the reflective surface will behave like a perfect mirror or will it dampen the color due to its own properties, like we see for a shiny metal or plastic. If it is a totally colorless glass-like substance that is a perfect mirror, then it would show the object exactly in the same color that the object is in. But suppose this is not a total fully glass-like material, suppose it's a shiny metal-like surface, then the metal has a color of its own, so that will change what reflection is shown here, all the color that would be produced here. Also notice how epsilon, the use of epsilon will occur here. Similar to how we had the phenomenon of self-shadowing, we can also have a phenomenon of self-reflecting. That is why we would need epsilon. The premise is almost similar to what happened before. The intersection that would happen at first, the primary ray that would at first hit the reflective surface, might hit the not the surface but inside the surface due to some rounding errors. The point that might be found may be inside the surface. And then the second ray that you were supposed to cast towards the other objects in the scene might hit the surface of the object itself at first. And since if you do not have any particular material defined for it, any particular color defined for it, that particular point wouldn't be able to see the color of the outside objects, rather its own color, which is black. So you might have some black dots or some any other colored dots here. For that, we need to avoid self-reflection, and so we need to displace the secondary ray coming from here by a small amount, for which we would need to use epsilon. So if we had a perfect mirror reflection, then the angle between the normal and the reflected ray would be equal to the angle between the normal and the incident ray. This is what we know from physics. This is just basic law of reflection. That is, incident angle should be equal to reflected angle. And for this, we need to use the negative of the normal. When you are considering in terms of vectors, here we would need to use the negative of the normal for calculating the reflected rays vector. The reason for this can be actually understood if you recall the discussion for particle collisions in our previous lecture on the topic of collision detection and response. We already talked about how this particular thing would happen for particle collisions. So the basic idea here is that notice how this particular vector can be obtained by two things, that is this vector plus this vector, using the triangle law of addition of vectors. This particular vector will be this vector plus this vector. Again, this vector will be obtained from another triangle, that is this vector v plus negative of this is not exactly n, this was the negative of n. The way we are actually obtaining this is by using the projection of v on n and then multiplying with n. So this is minus v dot n times n, and v plus minus v dot n times n is equal to vt, and then vt plus minus v dot n times n, that is using this another time, we'll get this vector r. So that is how we get v minus 2 v dot n times n. This particular vector comes twice here. So that is all for how reflection would be introduced into ray tracing. In the subsequent lectures, we'll be talking about refraction. So this will be the end for now, for this part 1 of this lecture. Thank you for your attention.